This is actually part one of a two-part series. We're going to be looking at thermal testing of existing hydronic circuits. And in a nutshell, what we're trying to do is determine what kind of output can an existing hydronic circuit create when it's operated at different temperatures uh, compared to what it was originally designed for. And the idea is there are many, many circuits out there now, systems that were designed around higher water temperatures, primarily using boilers as their heat source. If we're going to integrate either an air to water heat pump or a water to water geothermal heat pump, typically we want to operate those at lower temperatures to get higher coefficients of performance. So we do need to know, though, how much heat we're going to get. If we were to take a circuit that was designed around, let's say, 160-degree Fahrenheit water temperature, and we choose to operate it at 120, obviously the output's going to be less, but how much less? And there are different ways to approach this. We're going to get into those in detail, but I just want to kind of give you the incentive why we're doing this. Let's say we want to get into racing, car racing, and we decide to go to Italy and buy a Ferrari engine like this. And I've had an opportunity to actually see one of these engines. They sell for about $500,000. Beautiful piece of engineering. So we buy this expensive high performance engine and we put it into this. Okay. This was, I believe, either a 56 or a 57 Chevrolet. And it was a good car in its day. But if you look at that engine and you look at that body, you know that you're not going to get a Formula One racer when you put those two together. Okay. The chassis, the body, the drivetrain, everything in that Chevrolet just isn't designed to make efficient use of the power in that Ferrari engine. So what's the analogy? Well, let's say we use a heat pump, and it really doesn't matter whose heat pump it is. This happens to be an air-to-water heat pump, but the same logic would apply to a water-to-water geothermal system. We have a engine, if you will, a thermal engine that's capable of high efficiency, high performance. And if we match it up with something like this, staple up tubing, tinfoil or aluminum foil being used for heat transfer plates, inadequate insulation. We could spend all afternoon looking at these kind of house of horrors photographs. We're definitely not going to get first place for the best hydronic system. Instead, we're going to probably get complaints from our customers. So we don't want to do this. We can't match a high performance heat source with a poorly designed or an inadequate performance distribution system. And as I've stressed in past webinars, just installing that heat pump is not going to fix those existing problems. Okay. Now, the two approaches that we've got to analyze these circuits, one is theoretical. And I enjoy the theoretical approach. There are ways to model the hydraulic performance of a system. If you know what the pipe sizes are, the pipe lengths, how many fittings, what circulator you're going to use, what type of heat emitters, what type of heat source. There are analytical models that we can create for all these portions of the system, and we could run a simulation. And that's okay, but it requires a lot of on-site work to accurately simulate a system. We really have to know every part that's in that system, every fitting, every length of pipe. We also have to make some assumptions, like we don't have fouling inside a heat exchanger, or we don't have a circulator that isn't performing right on its pump curve because there's some type of debris in it, and so forth. So there's potential complications with trying to take theoretical models of components and put them together. Okay. The calculations are all doable. We would use a computer to process them. Trying to do these calculations by hand is a non-starter, believe me. So again, we rely on a lot of different properties. We'd even have to know what is the percentage of antifreeze in the system, if indeed the system uses antifreeze. That's going to affect viscosity and density. That's going to affect flow rate and so forth. Now, the other approach is to actually measure it, and that's the one we're going to focus on today. We need to measure temperatures and flow rates. It still requires some on-site work, but as it says, it captures the effects that might not otherwise be found by theoretical analysis. If we did have a heat emitter that was partially clogged for whatever reason, that's going to be captured in the measurement of the performance of that system. Whereas in the theoretical model, we would have no way to know if that heat emitter had any type of fouling in it. It is going to reduce the number of calculations. The calculations are relatively simple, okay? And again, we're getting results based on actual versus rated component performance. If the, again, circulators, every circulator has a published pump curve. On a good day, you can think about plus or minus 5% repeatability on that pump curve. If that pump's been in service in a dirty system, all bets are off as to what the actual pumping performance is compared to its theoretical performance. Okay, so let's talk about measuring the performance of the system. There's basically two physical quantities that we need to measure, and then we will use those quantities to make some simple calculations. We need to know the temperature drop around the circuit, and we also need to know the flow rate going through the circuit. Okay. So we're going to combine those along with the physical properties of the fluid. Now, we do have to know what fluid is in the system. If it's just water, that's easy. If you suspect there's antifreeze, there's simple instruments called refractometers that you can get that at least give you an estimate of what the concentration is. And then, as you'll see in a minute here, there are some graphs that you can use to come up with the fluid properties. So temperature measurements. This is an instrument that I've owned for quite a while. It's a Fluke dual channel thermocouple meter. It's affordable. These run about $400 now. They're very high quality. And up at the top, you can see those two leads over here. And the very tip of those leads are thermocouples. Here's a zoomed in view. So that's actually the very small, it literally looks like a tip of a wire. It's about 1/4 of an inch long. That's where the temperature is going to be measured. One nice thing about these, they're relatively inexpensive. These meters are accurate to within about 1/10 of a degree Fahrenheit, which is acceptable for our purposes. And they're very low thermal mass. In other words, if you put your fingers on that sensor within seconds, it'll change from room temperature and stabilize at whatever your skin temperature is. So it can respond very, very quickly. Okay. As far as mounting it, it's easy. Here's a copper pipe. The thermocouple just goes up against the pipe. I like to wrap it with a piece of electrical tape just to hold it in good contact with that copper tube, and then put a small piece of insulation over it. That just minimizes the tendency to measure something between the pipe surface temperature and the surrounding air temperature. And actually, that piece of insulation is a little larger than it has to be. The idea is, though, the copper tube in particular, there's extremely small temperature drop between the fluid on the inside of the pipe and that external sensor. And you're going to be measuring temperatures in two locations. If they're both strap-on locations like this with the same type of sensor, the slight difference between the water temperature inside the tube and the temperature on the exterior of the tube, that's essentially gets canceled out mathematically in the calculation. Now, flow measurements. This has always been the challenge over the years, is how do I get a reasonably accurate measurement of flow? There are flow meters. Specifically, they're called rotometers. They're a tapered tube that has a wire and a float. And as the flow rate increases, the flow goes by the float in the meter, and it actually lifts that float to a certain location, and that has a calibrated flow rate. It's a very analog device. They've been around for quite a while, but quite honestly, very few hydronic systems are going to have these flow meters installed. They simply, in most cases, they add cost. They are more delicate than some installers are used to, so they can be broken. But over the last couple of years, we've come across this type of meter. This is an ultrasonic flow meter. It does not penetrate the pipe. It straps onto the pipe. And you can see there that in this particular case, it's reading about 3.1 gallons per minute. So again, it can resolve to about a tenth of a gallon per minute. Here's another view. This stainless steel frame in the back. There's 4 screws. You just back those screws out and saddle the frame around the pipe, put the screws back in. You can mount that frame in about 30 seconds with a little battery-powered screwdriver, and then the instrument itself snaps into that frame. And ultrasonic flow meters down here, again, this technology's been around for quite a while, but it's always been very expensive, several $1,000s for something with this type of accuracy. And like many things, the price and the performance has the price has come down substantially for uh, actually a very high performance instrument. They work by sending ultrasonic pulses in 2 different directions, one against the flow and one with the flow. And they correlate the difference in travel time from where that pulse is emitted to where it's intercepted. They correlate that with both the upstream and the downstream, what are called flight times. And that difference in those flight times in that measured signal is a very tight correlation with flow rate. And just to give you some idea, you can actually find these on places like eBay. And I just looked up one. This is a brand new meter, about $320. Retail, these are more expensive. They can run $800 to $900 depending on what the pipe sizes are. And they do make these meters to go into saddles that will go on different size pipes. For example, 3/4 inch and half-inch pipe can be handled by one saddle, but there's a different saddle that'll go to 1 inch and 1.25 inch pipe. And obviously, the bigger pipe saddles are add a little bit more cost. But for whatever reason, these are sold pretty much directly from Japan, where they're manufactured on eBay. So for a few $100s, this is a professional quality instrument. You can take it with you. You don't have to leave it on the job site. And it is powered by, I believe it's a 12-volt DC power supply, just a small little black box transformer. So if you've never had a good instrument for measuring flow rate in circuits, I'd recommend you take a look at this brand, Keyence, and it may be a tool you want to add to your toolbox. Now, it's also important to understand that hydronic systems, when they operate, very often they're not operating at steady state conditions. Steady state means we're at conditions where temperatures and flow rates are not changing. And this graph just shows you that depending on the thermal mass of the circuit, uh, it may come to a steady state condition quickly, literally within a few minutes. But as you increase the thermal mass of the circuit, and that could be by larger pipe sizes, or in particular, if you're going to something like a cast iron radiator versus a piece of fin tube baseboard or a fan coil, or in an even worse case, a 4 or 6 inch thick concrete slab, the more thermal mass you have, the longer it takes to get to steady state conditions. And we need to be at or very close to steady state conditions to get these measurements and have them mean something. If we take a snapshot during an unsteady state condition, we're getting a snapshot of the performance at that point, but that isn't necessarily going to indicate how it would perform at other conditions. So, as it mentions here, uh, relatively short circuits, small pipe, low thermal mass heat emitters like fin tube or fan coils, they can reach a steady state condition in 10 to 15 minutes. If you get into longer circuits, bigger piping, you get into things like cast iron radiators, it could take an hour or two. And if you get into systems with concrete slabs, especially if you're bringing that slab up from a cold start condition, it could take several hours to reach steady state. But there's an important point that I want to make here. The circuit doesn't have to be at its typical operating temperature when measurements for flow and temperature drop are taken. We can take these measurements at lower supply temperatures as long as we're near a steady state condition, and then we can extrapolate that performance to other temperatures. And again, we'll cover that. So if the circuit is achieving steady state conditions, it's going to do it quicker when we have lower supply temperatures because we simply aren't going to push the thermal mass up through a much wider temperature range. And I'm going to suggest we only have to heat these circuits up 20 to 25 degrees Fahrenheit above room temperature in order to allow it to get conditions, temperatures, and flow rates that we can then use for making calculations. Now, another thing that can complicate this testing, on-off heat sources. If you take a typical boiler, it might have an oil burner on it, or it might have a gas burner, but it's just an on-off device. What you get is cycling. A boiler that's controlled as an on-off device typically is not at steady state. If you look at that graph there, you'll see that up and down orange curve, that tends to show what the temperature cycling is for an on-off heat source. Ideally, we'd like to have it produce a temperature right along that light blue line, a steady state temperature. But because we can only turn it on and off and we can't modulate its heat output, we get these differentials. But again, I'm going to show you a workaround on that. Okay. One would be to try to reduce the differential as small as possible. That's going to decrease the amplitude of that swing in temperature. That's still not an ideal condition, but if you were to test under a condition where you're cycling between, I'm picking a couple numbers here. Let's say the boiler turns on at 110 and it turns off at 115, and it does that repeatedly. Your average temperature would be about 112.5, and that would be a temperature that you could use. But we're going to look at another way to actually add heat to these circuits where we don't have to use the boiler. Now, let's say we do have temperature measurements and we do have flow rate measurements. Many of you have seen this calculation before, that BTUs per hour is equal to 500 times the flow rate in gallons per minute multiplied by the temperature drop of the circuit in degrees Fahrenheit. And I put that number 500 in red to emphasize a point. That is, first of all, it's based on water, not a mixture of water and antifreeze. And it's also based on relatively cold water, 60 degrees Fahrenheit. Why do I say it's based on cold water? Well, the density and the specific heat of water change with temperature. Specific heat doesn't change much, but density definitely changes with temperature. So I'd like to emphasize that this equation, it's easy to work with. Many times you can do the calculations in your head. If you have, for example, a delta T of 20 degrees Fahrenheit, multiply 20 by 500, you get 10,000. So it says the output of the circuit would be 10,000 times the gallons per minute flow rate through the circuit. And these kind of approximations have been used for a long time, and they're reasonable, but there is a more accurate way to do it. And this formula, if you look at it, instead of 500, you see in those square brackets, 8.01 times D times C, where D is the density of the fluid that's in the circuit at the average temperature that the circuit operates at. And C is the specific heat of the fluid, again, at the average temperature that the circuit operates at. So what those terms, density, specific heat, and the 8.01 is just a unit conversion factor. This gives you a more accurate representation of what's called the thermal capacitance of the fluid, the ability of the fluid to absorb heat. And then the flow rate would be in gallons per minute, and the temperature drop, again, would be in delta T. So you're probably thinking, okay, where do I get density? Where do I get specific heat? Well, there's two graphs that you can work with. The upper one gives you density in pounds per cubic foot for water and 2 concentrations of propylene glycol. If you were working with, for example, a 40-degree concentration, you have to interpolate between the 2 curves. The lower one gives you specific heat. Now you can see for water, the difference is very slight. In most cases, you could treat the specific heat of water as just 1.00, and that would be BTUs per pound per degree Fahrenheit. But for propylene glycol, depending on its concentration, you can see the specific heats definitely are lower for one, and they also vary with temperature to a much greater degree than does water. So as we mix antifreeze into water, we're actually decreasing its thermal capacitance. We're decreasing the ability of the fluid to absorb heat, and we need to account for that when we make a calculation. So we're actually going to be using this lower formula as we proceed from data into calculations. So let's do an example here. Let's say we've got this circuit, and I've grayed out one circuit. Let's say we're looking at circuit 1, and you can see we've got the temperature being read here at the supply and the return. So we have a delta T on that circuit. We're making the assumption that these manifolds are short. Okay, so effectively our boiler outlet temperature is the same as the temperature right here. And then we've got our flow meter strapped onto the pipe, so we've got our flow. And here's just the data we got. The supply temperature was 120.6. The return temperature was 108.1. Our flow meter indicates 4.2 gallons per minute. And we know the circuit operates with a 30% solution of propylene glycol. It says estimate the heat output. So the first thing we do is we go back to those graphs. Well, let's get the average circuit temperature first. So we just add the 2 temperatures, the supply and return, divide by 2. That gives us an average of about 114. Then we go to the graphs. And there are formulas for these curves, but the graphs are easy to work with. You just basically find that temperature. You go up to the curve for 30% glycol, and you can read the fluid properties on the vertical axis. So what we have a density of 63.5 pounds per cubic foot. Specific heat, 0.935 BTUs per pound per degree Fahrenheit. So we just plug all our numbers into that formula, the 8.01 times D times C, multiplied by flow, multiplied by delta T, and it works out to just under 25,000 BTUs per hour, so we just round it off. So there's an example of how to work with fluid properties, flow rate, and temperature drop to make a calculation. Now, it says measuring circuit performance using an external heat source. Rather than the boiler or the heat pump or whatever else is our normal heat source, we're going to make a change. And the way we're going to do this is create a pretty simple apparatus. It's based on the fact that almost all hydronic circuits today, where you have a circulator, you have isolation flanges or you have ball valves or gate valves so that you can isolate that circulator and remove it. So what we're doing is here's the circulator. We're just simply closing those 2 isolation flanges. We're removing the circulator and we're putting in this apparatus. And I'll zoom in on it a little bit here. You can build this with a set of bronze circulator flanges. You can solder in a short stub of copper tubing, put in what's called a baseboard T. That's a 3/4 by 3/4 inch by 1/8 inch side tapping. These are commonly used to put an air vent at the high point in a fin tube baseboard. And you're going to do the same thing on the other side. Now, next month, we're going to get into this right here. I'm not going to take much time other than tell you this allows us to measure the differential pressure across the circuit at different flow rates. Next month, we'll get into exactly how you use that to come up with the hydraulic performance of the circuit. Now, let's go on. I want to talk about what is down here. First of all, we're going to work with a block here. And again, go on eBay. You can find these for sale. You could probably find these at your local auto supply store. They're designed to heat the fluid in a vehicle when it's very cold, and it's simply a 1,500-watt, 120-volt electric heating element in this, polymer shell, and they cost about 75 or $80. It comes with a line cord and a plug, so that's going to be our heat source. We're not going to use our boiler or heat pump. We're going to use this electric heat source to inject heat into the circuit. Now, we can control that. We can control it using a 2,000-watt rated dimmer switch. And I want to emphasize, you want to make sure you get one that's rated for at least 1,500, but preferably 2,000 watts. Don't buy one that's designed for 100-watt or 200-watt. These are solid state components, and these can vary the electrical power that goes into that heater. So we have control over the rate of heat input. We also have very stable heat input. If we set this thing up for, let's say, 1,000 watts of heat input, it's not cycling on and off. It's basically going to just provide a stable 1,000 watts. Now, to measure that, we're going to use a fairly inexpensive meter. I'm sure some of you have probably seen these or worked with these. It's actually called a kilowatt. Three different words there, kilowatt meter. These cost about $35 or $40. Designed to plug into a receptacle. You plug an appliance in and you can read wattage, voltage. You can read actually volt amps, and it can record energy use over time as well. We're simply using it as an inexpensive way to read wattage. So rather than measure voltage and current, which you could do, this will do the calculation for you. And then we're also including a variable speed circulator. This could be any, I would say an ECM circulator that has a speed adjustment range on it. So that's going to provide the flow, because remember, we've removed the normal circulator. Here's our flow meter. This can actually go anywhere in the circuit because the flow through this entire circuit has got to be the same at all locations. I'm showing it just as part of our apparatus here. And then finally, we're going to put our thermocouple on a return and on the supply. So we're actually measuring from a starting point here on the supply, what is the temperature drop around the circuit coming back? And I use a piece of hose here simply because it allows you to, flex this assembly around. So we'll call that our test apparatus. Again, there's our dual channel thermocouple meter. Here's our ultrasonic flow meter. So we're putting together a system here, an apparatus that can inject heat into the circuit, measure how much heat is being injected into the circuit, and then measure the flow rate and the temperature drop at that given rate of heat input, allowing us to do that calculation that we just did an example of. Okay. Here's one that a contractor built up. It's kind of an early prototype. It's a little taller and bigger than it has to be, but you can see there's the circulator they're using. Here's the block heater. They used, I don't know if these are washing machine hoses or what, with a pressure gauge up here. Here's the solid state dimmer, and here's that kilowatt meter. Okay, and again, there's the same photo. And remember, that test apparatus is certainly reusable. After you've done these tests, you're going to remove it, put the circulator back in place, and save it for the next job. So let's go through. Let's say we have a 4-zone, 4-circulator system, and we're going to prepare for a test. The first thing we want to do is to turn on all the circulators. We want all the circulators operating when we measure the flow rate in each individual circuit. The reason that we want them all operating is we want the maximum pressure drop through the common piping. So from the return header through the heat source and then out on the supply header. Remember, as you add more and more flow rate into that common piping, you're going to have higher pressure drops. What that is going to do is reduce the flow rate in those circuits. So we're measuring under, I'll call it the most conservative condition, the lowest flow rate in each of these circuits. And what we're going to do is move that ultrasonic meter from one circuit to the next, and you can do that relatively quickly, a minute or two in each circuit. we're going to get a reading on that what I call the as found flow rate. And I'm just simply showing here using a spreadsheet just to write down these flow rates. Okay, these are in gallons per minute. Now, we're going to put our apparatus in place. We're going to turn on the test circulator and we're going to adjust it so that the flow rate in the circuit we're testing is about the same as what we just did when we had all the zone circulators running. In other words, we're trying to simulate a condition that would occur in the system with the normal circulator in place, with all the other zones operating. And again, that's the most conservative, lowest flow rate condition. So we're going to dial in a flow rate. It doesn't have to be absolutely exactly the same, but it should be reasonably close. Then we're going to put some power into our electric block heater. I'm going to suggest starting with 500 watts of power input, and we're just going to watch and see how quickly does that circuit come towards a steady state condition. And can we warm it up so that the supply temperature is about 20 to 25 degrees above the room temperature? If we can't, we can put a little more power in, okay? So we can just simply dial in more wattage and bring that up so that we get about a 20-degree rise above room temperature on the supply side. Again, we want to let the circuit stabilize to a steady state condition, and we're going to read and record supply temperature, return temperature, the air temperature, we'll need that later on, and the flow rate in that circuit. Now, some of you might be thinking, well, what about what's happening with this flow going through this heat source that, this could be the boiler, for example, the normal boiler. Isn't that causing some heat loss? And yes, it is. And we're going to account for that. Okay. What we call the accounting for heat loss through the inactive heat source. Remember, for example, a cast iron boiler, when you just pump warm water through it, you don't fire it. It's essentially a cast iron radiator with a partially insulated box around it. It is going to dissipate heat through the housing, as well as it's going to create some convection up the chimney. And we need to account for that to get an accurate measurement, because under normal operation, that would not be happening. That the normal heat source would be producing a temperature rise rather than a temperature drop. And I'll show you how to do that. It's pretty simple. So we're going to repeat that procedure for each one of the circuits in the system. Okay. And then we're going to use the formula. Remember, we're measuring wattage on our kilowatt meter. So to convert that over to BTUs per hour, we just take wattage times 3.413. And that's, again, you could say, well, there probably is a little heat loss from the shell of this heater, and you'd be right. If you want, you could wrap some foam tape around that or something to minimize that. But we're in the ballpark. This is not National Bureau of Standards level of testing. This is getting us in the ballpark of what the circuit's going to do. Okay. Now, inactive boilers. If it's this situation here where the flow goes right through the inactive boiler, and we're using the electric heater to add heat to the circuit, this is losing heat. And that's what the little squiggly arrows represent here. So to know how much heat we're losing, we just need to measure the temperature drop from inlet to outlet. And we know the flow rate. The flow rate, I don't show it here, but the flow meter would be in the circuit. So again, we're right back to this same formula, 8.01 times density times specific heat times gallons per minute, and T in minus T out. Well, T in is the temperature of the fluid coming into the inactive heat source. T out is the temperature leaving. Hopefully, it's a very small number, maybe 0.1, 0.2, 0.3 degrees Fahrenheit. Okay. Now, if you have a ModCon boiler, or if you've connected a heat source using a primary, secondary type piping, ideally, you would just close off one of these flanges so that there's no flow going through that inactive heat source. If that's the case, you really don't have to do any of this calculation up here. So again, if the flow is going directly through the heat source, you're going to need this calculation. If you're, in a sense, bypassing the heat source during the test, you don't need that calculation. Now, The calculation is, if we again go back and look at 8.01 times specific heat times density times flow. Before, we just had the delta T of the circuit. That would be from supply to return on our test apparatus. Okay, that would be from this point over here, supply to return. But now we're subtracting the temperature drop across the inactive heat source. And again, this should be relatively small. A fraction of a degree Fahrenheit might even be possible, 0.1, 0.2, 0.3 degrees Fahrenheit. But by subtracting that, we're negating the heat loss from our thermal testing procedure. And again, I just threw the graphs in there for density and specific heat if you're working with that equation there. Finally, you want to keep things organized, and a spreadsheet is a good way to do it. You could make up some blank spreadsheets, put them on a clipboard and take these readings. I'll just walk through it. Let's say we have a 4-zone system. We got the existing flow in all those circuits. That was the as found condition. Okay. Here's the flow rate that we actually established in each circuit during the test. And you can see I purposely made them a little bit different. They're close, but they don't necessarily have to be exactly the same. Here's the power input in wattage measured on our kilowatt meter during the test, again for each circuit. Here's where we've converted it over to BTUs per hour by multiplying the 3.413 factor. Here's our supply temperature during the test for each circuit. Here's our return temperature. Here's the air temperature. Now, you might say, what air temperature should I use? I have piping in the basement. I have piping up above. This is kind of a judgment call. I'm going to say generally you want to use the temperature up above. And I say that with the idea that if you've got uninsulated copper piping running through an unheated space, you really should be insulating that piping. You're losing heat there. You could make a point that should I average the air temperature between the unheated space and the heated space up above? You could, but that average would have to be weighted based on how much heat is actually being lost in the unconditioned space versus how much is being lost from the normal heat emitters. So in general, it's going to be the air temperature in the heated space. Here was, since we're assuming we're going through an inactive heat source, we've got the temperature in and temperature out. And you can see here it's lost, in this case, 0.7 degrees Fahrenheit. Here's in this test, in this circuit, it only lost 0.1 degrees Fahrenheit. But we have that data. We've captured it. Okay. Average fluid temperature in each zone during the test. We've recorded it. Okay. That's just based on the average between the supply and the return. And then using those graphs, we write down the density of the fluid and the specific heat. Now you'd see these numbers actually haven't changed because the temperatures, the average fluid temperatures are all really close to each other. So to 2 decimal points of accuracy in the case of specific heat, nothing has really changed there. And then now we're finally ready to make that calculation. Oop, let me go back here. This calculation right here. Okay. Put all those numbers in, and then we come up with the measured heat output of each circuit during the test. Now, what remains to be done is to take this, what I call a snapshot of steady state performance on each circuit, and come up with a way to project that or extrapolate that to different operating conditions. And that's where we come to this very simple formula. This formula is actually one of 2 formulas that is the theoretical basis for outdoor reset control. And what it says is that the output of the circuit is approximately equal to some number, I'll just call it K, we're going to find its value in a minute, times the difference between supply temperature, supply fluid temperature to that circuit, and the air temperature around that circuit. And this is basically a proportion. In other words, heat output is proportional to the difference between the supply temperature minus the air temperature around the circuit. And when you graph a formula like this, you get a straight line. And here's an example. let's say we want to find this value of this constant K for each circuit. So based on testing, we've got a net heat output. And by net, I mean we've accounted for the heat loss of the inactive heat source. Remember, we took that small delta T across the boiler. We subtracted that from the main delta T across the remainder of the circuit. So we've got the net output of the circuit minus any loss from the inactive heat source. So we've got a 15,500 BTU per hour. Supply temperature was 125 at that test. And let's say that the air temperature around the heat emitters and hopefully most of the piping, 68 degrees Fahrenheit. Well, we got all the numbers other than the value of K. So to find that one unknown value, we just take this formula, we rearrange it a little bit. We just take the heat output, we divide it by the delta T, and there's our number for K, 271.9 BTUs per hour per degree Fahrenheit. So what does that mean? It means that circuit would dissipate or release, I'll round it off, 272 BTUs per hour for each degree Fahrenheit the water temperature at the supply side of the circuit is above the air temperature. So if we want to know, for example, the output of that circuit at 105 degrees rather than 125, now that we know the value of K, we just put 105 in, and let's say the air temperature, let's say we want to assume an air temperature around the circuit of 70, and we just run it through a calculator, we're getting roughly 9,500 BTUs per hour. So, and we can do this both for temperatures above and below what the test conditions were. So in a sense, we're just going up and down this line based on the temperature difference now. And the value of K really just sets the slope of this line. Higher values of K, you're going to get a steeper line. Lower values, you're going to get a shallower line. But it's always going to be a straight line. So that's how you would do it. And now you've got a tool that would give you a way to estimate that output at lower water temperatures, especially if you're working towards higher performance with either air to water or water to water heat pump. Okay. So with that, I've gone pretty quickly, but I'm going to go back to Kevin. I think we do have some time for some questions, and then we'll talk about what's coming up next month.
Yeah, got some pulled aside here for you, so we will jump into some of the Q&A. First one is, where can I buy one of the Kayens flow meters?
Yeah, I would tell you to start on eBay. I'm not sure why, but there are quite a few sellers in Japan that sell brand new Kayens meters, and quite honestly, they sell them quite a bit less expensively than if you were to go directly to. There are dealerships in the U.S. and you can go any purchasing channel you want, but another engineer that I've worked with on several projects, he's constantly looking at eBay and buying up these meters as they come available.
What about how accurate do the measurements have to be?
Well, we're measuring flow rate to accuracy. It's plus or minus 3%. The Kayens meters are rated at plus or minus 3% of the reading. So if it was 10 gallons a minute, it would be plus or minus 3%. The temperature readings are within a degree, within 0.1 degrees Fahrenheit. That's a reasonably good accuracy for the amount of money we've invested in the test apparatus. Now, there are devices that could get us to 1/100th of a degree accuracy, and I'm sure we could probably find flow instrumentation that would do a little bit better than plus or minus 3%. But just to give you a comparison, and I should mention the two things here. Most balancing valves that have pressure taps on them, they infer flow rate by taking a pressure drop across an orifice. Many of those are in the range of plus or minus 10%, some even plus or minus 15%. So this Kayens meter is definitely more accurate than some of the balancing valves are. Another question that comes up, what about circulators that have direct flow rate readouts? I've talked to circulator manufacturers about this, and I'll just share with you what I was told. If it's new, If it doesn't have dirt in it, if there's no, magnetic, if there's no, uh, what is it, magnetite on the rotor, if the pump is clean, and if it's operating to the left of its maximum efficiency point on the pump curve, they say plus or minus 5%. Um, Again, that's what the manufacturer is telling me. That is not as accurate as the Keyence meter. So for a test apparatus that you might have $1,000 invested in, this accuracy is good. And remember, we're making estimates for the performance here, just like an estimate for a heat load. It's not, we're not trying to get things out to 3 or 4 decimal points of accuracy. We're trying to make a reasonable assessment of what that performance would be at lower temperatures. So we have an idea. Yes, the heat pump is a viable product here, and what kind of performance can we expect from it at these lower temperatures?
Thanks, John. Can I use thermistors rather than thermocouples for the temperature measurements?
You can. You can get thermistors. Many of the sensors that are used with hydronic controls today, for example, Tecmar or HBX controls, those are thermistors. Now, um, just so you know, those thermistors, a thermistor bead is tiny. It's literally the size of the head of a pin. When you buy a sensor that is typically used with something like a Tecmar or an HBX control, the thermistor is actually in a little cylinder that has a potting material in it. And they do that simply because that it allows for a little bit rougher handling. You can buy thermistors online that are much, much smaller, and they could be taped onto the pipe. Now, here's the thing. They have very light gauge wiring, and I mean like 30 gauge wiring. You have to be gentle if you're working with these. The biomedical industry uses thermistors that are very small. They're relatively inexpensive. They're $10 to $12 a piece, something like that. But yes, you can use thermistors. And the smaller the thermistor, the faster it's going to come to a steady state condition. When you have a typical hydronic system where the conditions are changing relatively slowly, the thermal mass of the sensor is not as critical. When you're trying to get this circuit to steady state as quickly as possible, the lower the thermal mass of the thermistor or the thermocouple, or for that matter, what's called a RTD temperature sensor, the better. So yeah, you can definitely use thermistors.
Got another one here. I was asked, can you briefly talk about best locations for attaching the thermocouples and flow meters? Is it best to measure on the main supply and return near the heat source?
I would say the beginning, I'm assuming you've got multiple zone circuits. I would put the supply sensor on the beginning of one of those zone circuits and then the other one on the return side of it. You could put it on a return header. Again, I'm making assumptions that the headers are pretty short. A couple things. If you're going to mount one thermocouple onto a copper pipe like I showed with a piece of electrical tape, and you could use a zip tie, I suppose, to hold it in place. Do the same with the other sensor. Don't mix, for example, don't put one sensor on a copper pipe and put another sensor on a steel pipe, or even worse, a PEX pipe. You're going to get a different temperature gradient across the pipe walls. When you mount the sensors on the same type of pipe in the same manner, the slight difference between the water temperature inside the pipe and the external surface temperature of the pipe, that cancels out in the math. But when you have different pipe materials, that cancellation isn't necessarily accurate. So, um, as far as mounting the flow meter, typically they don't want those flow meters mounted like right on the discharge of an elbow. Ideally, I would say 10 pipe diameters downstream of anything that could cause disturbance in the flow. The Keyence meter, one of the nice things about it, it will actually alert you if it has an unstable flow condition. Rather than give you a false reading, it'll basically give you a message, that the flow is not stable, move it to another location. As far as the flow rate, in theory, you could mount that anywheres in a circuit. The flow rate is the same in a circuit, whether it's upstream of the circulator, downstream of the circulator, upstream of a heat emitter, downstream, it doesn't matter. As long as it's in the same circuit, it's going to have the same flow rate. Typically, you're going to try to mount it in a mechanical space rather than, crawling around through the building and mounting it somewhere else, simply because you're probably going to mount your thermocouples, relatively close to where that flow meter is, just for convenience.
Someone else just asked in relation to those calculations you were going over, would you adjust your circuit heat load calculations for ambient conditions to determine loads on colder days?
Well, you're talking about outdoor reset control. When you have that value of K in that calculation, you've got the ability to come up with what's called a reset ratio for an outdoor reset controller, because you know how much each degree Fahrenheit change in supply temperature will affect the heat output. So to answer that question, by getting that value of K, that was the last slide that I showed you. In fact, let me go back up here if I can. Once you have the value of K, you've got a relationship here. In a sense, you have a reset line. So yes, you can use that reset line to estimate what the output would be if you're using an outdoor reset control strategy in normal operation of the system.
Thank you, John. We got a couple more, so I think we'll have time to get to them. Let's see. Uh, how hot does the circuit have to be before taking measurements?
Well, I'm suggesting that you get supply temperature 20 to 25 degrees above the air temperature. And I'm making that suggestion because it minimizes the time to steady state. What is more important is not so much what the supply temperature is or how high it is. What's more important is steady state or very close to steady state conditions. You will monitor that delta T and basically wait until that meter tells you, at least for a minute or two, that it's not changing. Or if you are seeing a change, it's very small, like a tenth of a degree Fahrenheit. If you can achieve that, 20 to 25 degrees above the air temperature, there's no need to go any higher. Remember, on that, let me go back to that graph again. What we're doing is we're finding one point on this line. We know when we have no temperature difference between supply water temperature and air temperature, we're going to have zero heat output. We know this point for sure. We're finding another point somewheres, and then if we know a point here and we know a point here, that's our line. So don't take the circuit up any higher than you have to in temperature, simply because you're going to, unless you want to spend more time there waiting for steady state, 20 to 25 degrees above the air temperature where the heat emitters are is a good point to take the measurements.
Got a couple of people asking about if we're going to have a copy of the presentation to look back on, and the answer is yes. After tomorrow or Monday, not going to promise tomorrow, but tomorrow or Monday, you'll get copies of the presentation, this video, Q&A, a PDF of all the Q&A questions that we're talking about now. So yes, you'll get an email with everything you need.
Yeah, and that's good, because those graphs for density, those equations, so forth, you can reference back to them.
Yep. We got 5 minutes or so here. Let's do, what is the pressure gauge and tubing at the top of the test rig for?
Stay tuned. We're going to talk about that next month. And I just very short summary. The pressure gauge and the two little ball valves up at the top allow us to get a differential pressure across the circuit, specifically between the supply flange of the circulator and the return side of the circulator, return flange of the circulator. Now, if we know that, and the way we use that, basically, we open one of those little ball valves at a time. So we get a pressure on the return side. Then we close that valve and we open the valve on supply side and we get a pressure there. It'll be higher. And so we have a delta P. And we also have the flow rate under that condition. And if we take, um, if we simply adjust our test circulator, that's that variable speed circulator. If we adjust that to different flow rates and take different delta P readings, differential pressure, we can create what's called a circuit head loss curve. And that circuit head loss curve, I've for years referred to it as the fingerprint of that circuit from a hydraulic standpoint. Let's say that we've got a circulator and we're wondering, should we put a bigger circulator in here for some reason? Maybe somebody's complained there's a baseboard at the end of the circuit that isn't quite getting hot enough. And you might say, well, gee, what would happen if I went from, let's say, a 007 to a 0010? I'm just picking numbers here, circulator. If you have that circuit head loss curve, you simply plot the pump curve of any circulator you want to try. And where the pump curve crosses over the system head loss curve, that's called the operating point of that circuit. It tells you the flow rate that you will get in that circuit with that particular circulator. And then we can make a decision. Do we want to go to a bigger circulator? Is the circulator we got adequate? What if we even went to a smaller circulator? So the portion of the apparatus that's up at the top is to get the hydraulic performance of the circuit. And if we had 2 hours today, we would go through that, but we decided to do it justice. We're going to break that up into part 1 and part 2. So I might as well go right into our next slide. Next month, we'll be talking about hydraulic testing of existing circuits, to complement today on thermal testing. Kevin, I think, did you have one other question?
I do. If you can answer it quick.
Sure.
What if I don't include the temperature change across the boiler that's not firing?
Well, if you don't include it, what's happening is you're actually taking data on a circuit and literally think of that boiler as another heat emitter. Okay, it's a heat emitter during the test, but under normal operation, it's not a heat emitter, it's a heat source. So you're introducing more heat dissipation into the circuit during the test than actually what's going to be there under normal operation. Again, if the flow is not going through the heat source, if you're connecting through, a hydraulic separator, or if you're connecting through a buffer tank or something like that, it doesn't matter. But think of a boiler. Again, I refer back to a cast iron boiler. It's a cast iron radiator with a jacket around it. And that heat loss is going to introduce error into your measurement, which we talked about accounting for today. How much? Honestly, I don't know. It isn't going to double the heat output of the circuit, I suspect, but it could affect it. Just guessing 5 to 10%. So you've got the instrument. It's easy. In fact, one of the other things you can do that makes it even easier, buy a couple extra thermocouples for your fluke meter and just put those thermocouples on the supply and return connections of the boiler. Once you've made your delta T measurement across the circuit, just unplug those two, take your meter over to your boiler, plug the other two in, and you'll get the delta T very, very quickly. So you don't even have to move the sensors if you have a couple extra thermocouples to work with.
Thank you, John, and thank you everyone for joining us. That's going to do it for us today. Don't forget to sit tight for just a moment. Once I end this call, you'll have our survey prompt again, and we'll appreciate if you guys can fill that out for us. Like I said, you'll be receiving an email in the coming days containing the Q&A, presentation slides, copy of the video, and a link to register for the next month's webinar, which John highlighted. It's July 24th. We hope hope this was beneficial to you guys and that you'll be able to join us again next month. Have a great rest of your day and a great weekend.
Thank you, everyone. Thank you, Kevin.
See you, John.